I want one to have some.
Yeah, that's allowed.
Okay. Thanks for coming and welcoming Doug Webb, who is visiting us as part of our distinguished acoustician series. And engineers and whatever Doug really is. And I've known Doug for about 20 years since I came here. And, Doug originally is from Ontario, is that correct?
Correct.
He told me when we were working in the field, he was from Hohen Sound, and I never could find that, and it took me a while to figure out where that is, which is Owen Sound. Not being a linguistics expert, I didn't quite get that. And then after college in Manchester and in Queen's University, Doug went to the Ferranti Electric Company, also in Manchester, England, and then from there to the Olivetti Company, and I don't know actually where it was located, but he worked for Olivetti for 6 years before coming to Woods Hole in 1962 to the WHOI, and he was on the technical staff of in the research branch until approximately 1982, when he founded the Webb Research Corporation, which is a Falmouth company and is now one of the sturdy legs holding up the Teledyne Marine conglomerate. And anyway, we've invited him here because of his vast experiences. We'll try to learn from some of his adventures. Thanks for coming.
Okay. Well, it's great to be invited. Thank you for having me. I don't quite know how the conversation here should go, but I'm ready to tell a few stories about adventures and inventions and learning about the world, and glad to entertain any kind of questions. The discussion will be primarily about engineering, and I thought I'd try and trace a current about how we have depended so much on outside technologies becoming available to us. The thread of the story that I think of really starts with the work of John Swallow in the mid-50s. John made some rather simple neutrally buoyant floats to look at the movement of water deep in the interior of the ocean. And that turned out to be a very important thing to do. At the time, in the mid-50s, the model of the deep ocean was that there was a slow, almost imperceptible motion of water southward from the polar region towards the temperate and tropics. He found that that wasn't the case. He put the floats in the water and they would move off somewhere at a higher speed that he could reasonably track them for very long. Come back a few weeks later, he was working from a Woods Hole sailing ship out of Bermuda. The ship was the Ares, and it's often called the Ares experiment. Back in a few weeks, put some more floats in, they'd go off in a new direction. He wasn't able to really do a great deal more than that, but it presented a mystery that the ocean was behaving entirely differently than people thought. And we worked to, he had discovered the mesoscale. Technically, it was kind of an admirable effort. He was using technically a nickel scroll for the sound transducer, a scroll about this large, an external winding on it. To the electronics were a 300-volt battery and a single gas tube, discharge tube inside that was just oscillating and sending a pulse every few seconds. Well, following that work, in the early 60s, I had started working here at the Oceanographic and worked on evolving those short-range neutrally buoyant floats. We introduced, for the first time, the then fairly new PZT, lead zirconate titanate transducers. It was a ring transducer operating at 4 kilohertz. We introduced accurate timing, and it was, as far as I know, the first instrumentation to come from here using transistors. Not yet integrated circuit chips, but just individual transistors. Well, I don't think that group of short-range floats really improved our knowledge of the ocean a great deal, but there was a kind of an offshoot of that which was rather interesting. Part of what I thought is interesting to say is just how things get to happen. I had in my notebook some ideas about measuring vertical current in the ocean. Well, no one thought much about vertical current at the time. I'm not sure that it's a big question right now, but I thought, well, if we take a neutrally buoyant float and put vanes or propeller-like vanes on it, it will rotate if water is moving up and down past it, and we can measure the rotation with a compass. I didn't think it would go anywhere because at the time the physical oceanographers were really very conservative, very distrustful of new electronic instruments, and they weren't entirely wrong. They weren't all that good. As I say, we had just managed to introduce using transistors, and stuff before that, which people had tried to use vacuum tubes. You can see there was a real problem with that. However, by very good fortune, the ship Crawford was in the Caribbean and was supposed to do an air sea experiment. The equipment wasn't ready. There was a rush to find someone to use the ship, so Val Worthington arranged that we would take the ship. In 6 weeks, I designed and put together and shipped 4 of these new vertical current meters, and they worked very well there. That experiment, we learned some things, but where it really paid off is we then took the vertical current meters to the Mediterranean in the winter for a first look at convection when the surface water becomes sufficiently dense to sink through to depth and forming new bottom water. We did that in 69 and 70, and for the first time we saw steady vertical flows of 10 centimeters a second, hour after hour. Hadn't ever seen or measured that, and it would be very difficult to approach it with anything other than something like a vertical current meter. The usual density measurements don't tell you anything except that overturning would be possible, but doesn't tell you how much or how fast. So that was a nice accomplishment out of those short range floats.
Doug, I have a question. Were those tracked?
Pardon?
Were those tracked, the VCM?
The
Acoustic
Yes,
tracked?
they were acoustically tracked, but we had to recover the data from them. You know, I think running through this story from here on is going to be several decades of just being really severely handicapped by any kind of data storage. The VCMs introduced for the first time data telemetry, acoustic data telemetry. Pretty primitive, but it did the job, worked well, and continued to be used that way for several decades. But the successful, to give you an idea of this whole business, the successful experiments on convection, we carried a paper strip chart recorder inside the instrument. And not because we were backward, there was really no other way to do it.
I know people that have photographed dials with cameras.
Yes. Well, altogether, those, although the John Swallow experiment had been very important, I don't think we learned a great deal except about convection with those short-range floats. But by the late 60s, I had started to get interested in whether we could make neutrally buoyant floats which would have a long life and be able to signal to land-based stations. And this is really what the beginning of the notion of SOFAR floats. I did this work with Tom Rossby, who was then a graduate student at MIT, and we put together 3 floats. Sandy would remember some of this stuff going on. We used a large sphere for flotation, and the sound projectors were large ceramic rings, 30 inches in diameter by 15 inches tall, resonating at 550 hertz. It's an interesting little adventure there. The first 2 that we deployed signals did not get through. Now I'll talk in a moment about the receivers that we were using, these ocean hydrophones cable connected to shore. That was, we had to do, if it's to get the long endurance. I didn't want to use ship tracking at all. So I had some hints that perhaps, it's very difficult to find out the performance of these phones, but I had some hints that we might be suffering from attenuation of the high frequencies in the cable. So we dropped the frequency to 300 hertz, operated the rings off resonance at a much lower output, and the third one worked. Well, that was kind of helpful because the next thing that happened was going to be the possibility of initiating what became the Mode 1 experiment. And in terms of, luck and things that have surprisingly good results. That was an interesting kind of thing. In the early 70s, there was in the United Nations a great deal of discussion about the law of the sea. Dom Mintoff, the representative from Malta, was in charge of these discussions, and as I understand it, the American ambassador made a very inept vote, and it upset a lot of people, upset them badly in these law of the sea discussions. So without much review or discussion, President Johnson made a television announcement that the United States was going to sponsor the International Decade of Ocean Exploration. And with some substantial sums to do it. And an interesting statement as well was it was an international decade of having nations join together to do this work. Well, Hank Stommel had for some time been thinking of, I'm sure he wasn't alone, but he'd been thinking hard about resolving the mystery that Swallow had unlocked in '55, and came forward with the notion of the Mode 1 experiment. Try to see what really was going on in the interior of the ocean. It was rather an exciting possibility. I think for the first time it required a considerable group of scientists working together to a common goal. That was not really the MO for most investigators, and it was quite a challenge. It worked out very well, but there was a lot of discussion. We really brought together the resources of a large number of people and occupied a piece of ocean and looked at it intensively. I apologize for many of you who probably read of Mode 1 and the results, but it opened the door to walk right through with the SOFAR technology. And that was, in a way, a substantial adventure. To start with, ocean data. What did we know about noise and attenuation in the ocean? There was remarkably little data, and what there was often in conflict. We had to master the use of these hydrophones, which were, there was another piece of very good fortune. At the time, acoustic surveillance of the ocean for submarines was a large effort and a very secret affair. You could get into trouble just by talking about it. However, by very good fortune, Gordon Hamilton, who was in charge of the SOFAR station in Bermuda, was one of those rare people who kept in his mind clearly what was classified and what wasn't, and helped us to get hooked up with what was some deep hydrophones of the Missile Impact Location System. The early missile tests, they landed in the Atlantic, dropped a SOFAR charge, and the impact was located by where these hydrophones could triangulate the position of that sound. So we gained access to those. That was crucial. It took a substantial effort, but it was just a piece of very good luck. The we had to sort out a signaling system, but the real problem was about a projector for these floats. It seemed pretty clear that we weren't going to move ahead with these 30-inch rings. They perform very well. They still a proper technology today, but very costly, a little bit fragile, but mostly very costly. So I set out to try and decide how to solve that big problem. It was a big problem, for we wanted a frequency of order 250 hertz. It had to operate at deep in the ocean, at the channel axis, and it had to be of good efficiency because it had to operate for months at a time on battery power. Well, there was really, as far as I could tell, nothing available that would meet those needs. So I talked to everyone I could find about that, and it's interesting looking back. There's some of the people were now probably known to many of you. I talked to, I got a lot of help from Ralph Willett, who was at the Underwater Sound Laboratory and was very well known at that time. And I had an interesting story chatting to Fred Hunt, who was in charge of the Harvard Underwater Sound Laboratory, which was a big activity during the Second War. I visited Hunt in his office on a day that he was cleaning up his office for retirement. And he was sitting there shuffling papers as we talked. And he reached in a drawer, pulled out a letter that he showed me. He said, "This is a letter that his father had received from Lord Rayleigh." Well, all of that didn't really advance as much about the projector. So but I think I essentially talked to myself about it. I said, you're at a fork in the road. Either you have to become a projector designer or abandon this line of research. So I decided to press on, and the person who I had talked to became a very important person, Claude Sims, who had worked at the Navy Acoustic Laboratory in Orlando and had started a small company of his own in Orlando. He didn't have an answer, but I thought Claude talked the most sense about this. And we worked together for quite a period of time, and Claude guided us to essentially the organ pipe transducer, a 12-inch cylinder with a ceramic, piezo ceramic bender face at one end, still in use today, simple and insensitive to pressure, reasonable efficiency, and that was really a crucial step of all those problems about making SOFAR work. That was probably the most challenging. We got 20 floats in the water for the Mode 1 experiment. We had an interesting field adventure during that time. On the projectors, the ceramic on the bender is isolated from the seawater by castor oil, was contained by a polyurethane membrane. There were 2 projectors on each float, and we found during the experiment that the cementing of the membrane to the aluminum was breaking down and letting seawater into the face. Well, by very good fortune, we had during this experiment we had people at 3 of the receiving stations, and the main line of collecting data was through a recording system which put it on a simple cassette recorder. That was the first time we really had proper recording medium. It would be laughable today. I think Sandy, you're very familiar with those. I think we had 1 megabit of storage. We thought that was a gigantic advance. But we had purchased some surplus Navy fax machines and converted them to record the signals in the stations, and we were able to the people in the stations were all keen hams, radio amateurs. They kept in touch with each other and kept in touch with the ship. We knew where these floats were that were giving trouble. They had a recovery system. We found them, called them up, took the face out, put it in the ship's lathe. It made a 60-ton manually operated press and pressed in polyethylene faces and refilled them and reballasted them, got them back in the ocean, and they went on working for another year or so. So that was an adventure with that. Once those became, I shouldn't say popular, but they became accepted as a part of the oceanographic toolkit, and probably order 150 of those floats were made before we finished. It led to a request to make a self-contained receiving station, and we could start to think about that because we had for the first time the capabilities of microprocessors. We had gone from making things with individual transistors to integrated chips, which would just be a flip-flop and gates. By this time, we had the microprocessors available. Al Bradley led that charge. We changed the signaling system from what we had used in Mode 1 to use an FM sweep, which was rather a novelty at the time. An 80-second sweep over 1.5 hertz with coherent summation at the receiver. And as that went ahead, Tom Rossby, who was still very much involved in all of this work, or was a major partner in all of this work, created the Reefus float system, which is still operational, where he essentially inverted the system and made moored transmitters and drifting receivers, and though that equipment is still being manufactured and used, That opening was made available to Tom because of the availability for the first time of microprocessors. The 1802, it would seem pretty primitive today, but it was a big and valuable deal there. Well, what comes next? A current of thinking that I was following in any case was kind of interesting. In a sense, it's a personal story, but it may be worth thinking about. I really was starting to think that the biggest handicap facing us about learning about the ocean, you know, a common kind of thing that people have meetings about, I thought the biggest handicap is the size of the research fleet. How are we going to really understand the oceans with 25 ships? And what is the next two kind of developments was an effort to cope with that. So in '82, as Tim has said, I started a small company here in Falmouth and set about trying to make ocean profilers. Initially they were called Alice, and they have other names now, but essentially they were neutrally buoyant devices which drift at depth in the ocean, ascend to the surface at intervals, and report their position and go back down again and keep on doing that for several years. It was an effort, you know, compared to so far, or the Reefus that Tom Rossby had been doing, to see us get global coverage, long-term coverage. They were initially aimed at providing trajectories of the current in the ocean, but they evolved to carry sensors. Initially, we were fortunate in that the Seabird system was available and of adequate accuracy and adequate low power. Low power runs through all of these devices because they work for long periods with battery powers. It was only possible because for the first time we had available the Argos satellite system, which could both tell us their position and handle the data coming back. So again, we were just exploiting these new things as they came along. First transistors, then ICs, then microprocessors, now Argos, and today using GPS and iridium has made all of that possible. That work on the profilers is done together, because everything takes a lot of people, and I'm not acknowledging all of the people that were involved, but the profilers were a joint effort with Russ Davis. It seemed to me that the profilers were pretty good, but they really work well when you've got a lot of them. You know, half a dozen profilers are nice, and that's worked out very well. Many of you may have seen these kind of plots, but that's where the world's profilers were on Monday. 3,214 of them. So now that says we've really made some strides to being able to monitor the interior of the ocean. It is still grossly undersampled, but it's not kind of outrageously undersampled as it was before that. So that worked out fairly well. Now, things like the profilers are only as useful as the sensors that they carry, and they are carrying an increasingly wide range of sensors. Well, that got underway fairly well, and following on that, we come to gliders. Well, I had thought about some long-range vehicle ideas and wrote up some notes in the 70s, but it really wasn't going to hang together very well. But in February of '86, I thought I could see a reasonably complete synthesis of the design of a glider to using thermal propulsion, that is, harvesting the thermal energy in the ocean to keep it moving. And as part of the adventure story, you know, it's interesting that I spent about 2 years talking about that to people who said, well, Doug, I don't think it will work, and if it does work, I don't think it's very useful anyways. However, once we demonstrated a glider working, it really took off, and for the first time, you know, the kind of conventional wisdom is a new instrument in oceanography usually takes something like 10 years to go from the kind of proof of concept to being an accepted tool. The gliders, after the very skeptical period, once demonstrated, they took off really too fast, that people wanted them, and we were in the environment of a small company and had to keep moving, and were shipping prototypes that we really hadn't got it sorted out. They're fairly complicated affairs, where anything like that takes a lot of internal smarts to look after itself. And you know, you try to get things wet and show that they're working, but that's really only a start. The ideas about thermal propulsion were bypassed by going with battery power. That made it simpler and more straightforward, and indeed to date we've made 200 gliders, and they're primarily battery powered. We've made a few thermal gliders. Todd Patterson and I have put together two which worked well but failed prematurely, and we're trying to overcome that. But they ran for 200 plus days, and we don't really know why they failed. Now, to wind up, I'll go back to acoustics. I've spoken to you about making the SOFAR floats with their 250 hertz signaling. Well, during that period, in the mid-70s, Bob Spindell, who was doing acoustics works here, said, well, what do you say we use something like this SOFAR float as a sound source for the research that I'm doing? They were doing transmission research using a moored projector at Eleuthera. And they were a little concerned that the Eleuthera source was getting old and might not last. So I told him what we could do, and the answer was, well, that's an almost laughable sound pressure level that will never be useful. But we decided to do it anyways, and put it out. They came back from the cruise and essentially said, that's great. We've got it under our control. We can move it around. We can do these tests in different places where we really want to do them. That opened up that possibility, and some Navy labs purchased sources for experiments that I never was able to find out quite what they were doing. But that changed, you know, in 1978, Walter Monk and Carl Wunsch described their ideas about ocean acoustic tomography. And there was, at Scripps they had been doing some essentially tomographic experiments with comparatively high frequency sources, and it was thought that really it would be best if they could get greater range, and there was a somewhat kind of forced marriage between Scripps and Woods Hole. For here we had these lower frequency sources, and we started on that. It was kind of interesting. In 1980, we took several sources to see, the first built specifically for tomography, and it was not a great success. They were built, they followed the general kind of SOFAR technology. They were built with a bandwidth, a phase code, and a bandwidth of 16 hertz. And when they came to looking at the results, it was clear, it would be very, I was surprised at the time it wasn't clear before the experiment, that was not enough bandwidth to resolve the individual arrivals. It was, however, those 1980 sources are still around and still being used.
Still being used for a lot of shallow water.
Yes. They were fairly rugged.
Good sources.
Big too.
So that led to the next major experiment. Carl Wunsch commissioned the building of 5 sources. We started in 1986, which were to be 100 hertz bandwidth. Now, I thought there's an interesting story there. I was myself very concerned about the 100 hertz bandwidth because we knew the organ pipe projectors did not have anything like that much bandwidth. But we built it on a kind of on a best efforts basis, and there were 4 projectors on the source, and they were all tuned to a slightly different frequency. And from my perspective, the world divided into 2 groups. There was a group who measured and looked at the performance of the system and said, this is hopeless, don't bother with it. And there was the group who put them in the ocean and did experiments and got quite good results. And in a sense, you know, they're all smart people, and they were all, to a degree, right. I don't know what others would say about it, but what I think really happened was we got quite narrow pulses, 10 millisecond. You could see a formal 10 millisecond band, but there was a long kind of sloping tail on the pulses, presumably from energy rattling around inside the projectors as they tried to change phase. I mentioned that just because there were 2 kinds of reviews, that we got some good experiments and it was formally a lousy system, but just what kind of lousiness was important, and that was not really sorted out. Does that make sense, Tim? Would you say it that way?
Sure. Would you like me to draw the pulse?
Yes.
This is the famous pulse.
Yeah.
Top right.
Yeah.
And this is 10 milliseconds.
Yep.
Yes.
And this is not. So they're half good.
Yeah.
Half the energy is usable and half the energy is not, so both groups were right.
Well, this story goes on just one more chapter, that how to cope with this. My own sense is we then spent a very long time looking for a projector that would do the job. And I've felt that the crucial problem was the statement we want to see resolve 10 milliseconds. Formally, that means you have to have 100 hertz bandwidth, 100 hertz bandwidth and a 250 hertz carrier. And at the time, I feel these are very personal comments about it. They might not stand up to widespread review, but the field was dominated by the wonderful success of jamming information down copper wires for modems and fax machines, and those were all phase codes. I thought to myself, man, this isn't going to work. See, if you've got a, this is not signals going down a copper wire. If you've got some large mechanical structure trying to change the volume of the ocean, and you ask it to suddenly change phase 180 degrees, that's the last thing it wants to do. We've been thinking of unconventional approaches, Walter Monk was kind of interested in unconventional approaches like sweep. Tim supported the notion by writing a nice paper about what could be done with FM sweeps. And we finally got some traction in two ways. That ONR gave us some money, a phase 1 SBIR to look at this, and Andrei Morozov joined us at Webb Research, and the two of us put together the sweeper, which the basic notion is just to deal with the problems I've just been mentioning by taking a highly efficient narrow band projector and mechanically retuning it to be resonant across a band, changing the statement that to get 10 milliseconds resolution, don't say you need 100 hertz bandwidth, say the signal must have energy across 100 hertz. Would you agree with that? Would you say that different?
That sounds right.
Well, it changed the way of thinking about it. So,
What you're saying is you don't need 100 hertz bandwidth instantaneously
yes.
throughout the transmission.
You need it over
You
some
need
period.
to occupy 100 hertz,
Yes.
but not all the
Have
time.
occupy with energy. So, in the last few days, Andrei has shown me that 6 of those sweepers have been recovered in the Philippine Sea. As far as we know, they all work. There is the 50-year story, folks.
Great.
Time for questions? You mentioned the use of PZT
Yes.
at an early time, but for some of these large, robust projectors, are you using any magnetostriction to drive these, or can you explain that?
Well, do you know Andrei there? Yes. Andrei and I talk about this from time to time. For a while, in the mid '80s, magnetostriction was a hot topic. That is, it had been improved. You know what John Swallow used in '55 was nickel magnetostriction, but nickel doesn't have as big a strain. So the terphenol materials came along at that time. They haven't resulted in for us many useful devices. Is that fair, Andrei? The Japanese made a low frequency projector. I understand that it cost several $1 million.
Is that the one that George Frisk used in an experiment, or is that
I
a
think
different
it might be.
It might be.
Hiroshima
The one,
University?
yeah, that one, it was accurate.
No, not Hiroshima, it is Jamstack.
Yeah,
Okay.
they were here, Andre, with George Peters.
I'd like to ask a follow-on question.
Nakana.
Macau,
Yeah, I'd like to ask a follow-on question. I should first say that it was just a marvelous presentation. Thank you. It's very nice to hear your recollections of this history.
There's an interesting story about PZT, lead zirconate titanate. It's to a degree an engineering and commercial story, but Cleveite developed barium titanate for the Navy. Big advance, you know, because before that it was Rochelle salts, the active material. But because it had been done for the Navy, it was available for public use. so they went ahead on their own money and developed lead zirconate titanate, which was an advance over barium titanate. And it was thought that, oh, you know, Clevite now have this locked up. They've got it patented on their own name. But I fell into working with Bob Carlson, who had just started Channel Industries, and he'd been a Second War naval officer, was starting a little business, so he just marched up to Clevite and said, "Can I have a license for PCT?" And they said, "Sure." Always pays to ask the question.
You mentioned terphenol, but there is now a gallium-based equivalent. I'm sure you know about it. Penn State's involved in galphenol, and this thing is strong under tension, not just compression. Is this maybe going to influence what you're doing?
Yeah, Doug, we discussed it. The material very close to steel and coming in machine.
Yes.
We didn't see a big advantage of, at least in our design, of changing. And there is a lot of additional problems of making high efficient magnetics. It's not so easy. You get efficiency in one direction, you're losing in another.
Ask a quick question. One thing that's kind of fun, I mean, after 50 years, you see evolution of things, and you get old in the process, but on the other hand, you get to see a lot. But the thing that's cool is you went from kind of from floats to drifters to gliders and tomography, and the question is, you know, where are these going to interconnect in the future? What's the future of these? Are they going to be individual? Are they going to connect? Where do you see people going with all this stuff, and include AUVs and whatever in it?
Well,
I mean, you've been looking in the future in a lot of technologies, and the future in a lot of these is linking with each other. And where do you see some of the links maybe? Where is it?
Jim, in my own head, I see it as kind of two paths. That I've been mostly engaged in what I felt was the problem of the size of the research fleet, which was the profilers and then the gliders. The recent work on the sweepers was really a leftover from so far technology, and a kind of frustration, because I thought we were asking the wrong questions about how to create the sound for tomography. It's only a fraction of what's required in tomography, and that kind of had a very long gestation period, and it got unlocked both by the support of Jan Lindberg at ONR, who gave us that crucial SBIR program, and by Andre coming, and I think the sweeper, neither one of us could have done it by ourselves, but together we made that work, and that's now largely in Andre's hands.
What about, to follow up on that, what about a mobile system? I mean,
Or combination systems.
tomographic mapping
Floats,
with gliders
gliders.
and floats. I mean, we've talked about that, of course, among the scientists for decades. You know, let's put receivers on Alice floats at the time and put a source out, and then we get a lot of paths and possibly map the
Very good
thermal structure.
resolution, fine structure.
Does it make sense? Is
for the
there a
source?
power constraint on that, or why aren't we seeing it? Have you thought about that, Doug?
I think we need to to talk about the design of an experiment.
It just
So
seems
you
a
see
lot
it as
of,
possible, it's just that the desire hasn't been there to build such a thing.
a lot of these technologies seem like there can be a nice interlinked synergy between them. I mean, they've all matured over the years to the point of, you know, they're all operational kind of on their own. But, you know, the combination seems to be an interesting question right now.
Well, running through what I've been saying is often it's just a fortunate set of circumstances brings together the outline of an experiment and the people and the technology.
Doug has often mentioned using gliders as station keeping them in just one location, but acoustically being able to talk to a moored instrument down deep and then using the glider to go up to the surface, transmitting the data. Is that sort of what you're...
Oh, no, I'm talking about, I mean, you know, Doug's been, the stuff he's doing has been done on kind of a global scale. And now when you talk about having a tomographic system that communicates with all these floats, or communicates with the glider system that's out there, or, you know, wiring all these different measurements that, you know, be in synergy with each other, it just seems to me that that's, you know, they're not separate technologies anymore. They become a bigger system, you know, a better system. But it just, you know, I was wondering if you were looking in those directions that, you know, see if there's anything more going on there. You know, it just seems to me that you've got four incredible scores right there in terms of, you know, the floats, drifters, you know, gliders, and tomography, and you know, nice interior ocean measurements. And it just seems like you know, a lot of the things you do after a while is you do cross-discipline. You kind of go interdisciplinary. So I was just wondering if you guys are kicking around on any of that stuff. What you're talking about seems more like a data communication problem, which is certainly part of something.
We should probably make a seminar here about it.
Yeah. Okay, Andre, you're on.
I just wonder how difficult it is to put the source in gliding. It operates for, say,
Source is too heavy for a glider. For an AUV, maybe we put sources in AUVs.
That would be difficult, you know, but
so using like resonant to the concept.
So you think on a glider even?
Yes, yes, I do.
Okay.
But how about power? The efficient. Low power. Wait.
No, tomography don't need really a lot of power. We're using reasonably powered 80 watts only.
Yeah.
Our sources are very efficient.
Yes.
It's, 80 watts is fraction of what of power would take pump to change buoyancy. And we will transmit probably a few times a day, so I don't think it's
Not a big deal.
not a big deal. We have such reserve, even on glider.
That's interesting.
And
but
you
to
can-
put a receiver on the glider is quite
Receiver
straightforward.
is easy, yes.
yeah,
Yes.
receiver definitely can be done. Yeah.
But with a
Same on float.
mobile source, tomography source, we
But
can go
see,
everywhere.
this is an interesting thing because the powered vehicles, you can put sources on quite nicely.
Yes.
And we've done, you know, and Andre's doing with us.
But yes, but you can calculate there is not a lot of power we're talking about. If you need to transmit with glider once a day on a longer mission, you need only 30 transmissions a month. And we definitely can transmit maybe 1,000 times with the battery what we have.
So it's not so bad. Yeah. It just seems maybe we'll take Andre up on doing a seminar.
Yeah, we probably will.
Well, the blessing that we've got is that Andre is at both places, and we talk regularly. So,
When you were trying to achieve the large bandwidth at low frequency, did you ever consider parametric sources just to have access to the bandwidth?
yes, of course. You want to address that, Andre?
No, probably not you.
Who wants to shoot it?
Yes. Not efficient enough.
Yeah,
that's
it's very low efficiency.
Yes.
Well, yes, of course, it's low conversion efficiency. However, the access to that bandwidth and the use of complicated signals allows you to use cross correlation, matched filtering to recover.
But we can make the same bandwidth with our sources.
Yeah,
Yes,
correct.
That's what they do.
Yeah.
That's what
It's all
we're doing.
cross-correlated, you can, either M sequences or sweeps
Because
are
you're
cross-correlated.
doing it linearly and.
Yes, yes. And
Yes.
Peter even telling you your source is too broadband, and you don't need so bandwidth.
Okay, and you don't have to worry about
Yeah.
Well, you know, the parametric sources, it always seems to me, are very attractive because of their high directivity.
Yeah.
That you can get them pointed at the destination so that their efficiency isn't as big a disadvantage. Wherefore, things like tomography, generally, we can't take advantage of directivity.
Or you do with an array if you have to, you do with the
Yeah.
receiver.
So that is very good for high frequency.
Well, no, the
acoustics.
parametric, I mean, you
Yeah.
look at the bottom a lot, because
Yeah.
you get low frequency, you penetrate the bottom, it's
Uh-huh.
directive, so that's a better use for it than tomography.
Different type of, different scientific goal, different.
Yeah.
Yeah. I understand from some of the work, current work on tomography, that there are still very much unresolved issues on timing, time of arrival, and speculation maybe about side load involvement, that is extraneous interference, extraneous arrivals. Do you have any comments on that?
If I may, you know, in this tomography business that Andre and I have done together, I primarily dealt with the engineering and Andre with the acoustics and science. What do you say about that, Andre?
Actually, can I take a little bit more information about your question? You're telling that timing is not really, I mean, it's like disturbing by some kind of effects not connected with the ocean, or what?
There are central problems with accounting for arrival times and differences due to multipath,
Okay.
which are unexplained.
Okay,
People are
I got
doing
it.
the detailed ray tracing or,
Okay, I got it now. Yes, there is, of course, there is global scale, which is moving these travel times according to tomography scale, and there is small scale scattering due to internal waves. And this is the main scale. There is two theories. It probably spice scale also disturbing a little, but this is mostly near the surface, and there is internal waves. And with John Colosi, we developed a very good theory about internal wave disturbing of these thermal arrivals, and you can read our papers, and we now don't need even Monte Carlo. We can use this very advanced stochastical differential equation approach. We can calculate by one run and getting so good agreement with Monte Carlo. It's just amazing. It's just less than 1%. So actually, it's very, very studied effect now, and we can predict. And we're now talking even about internal waves tomography, because for looking of this scattering of these separated arrivals, we can predict what was intensity of internal waves.
I have a question about bandwidth, and I remember you were talking about the 223 or 224 hertz sources with the 16 hertz bandwidth, which we use in shallow water, and then we can't resolve the individual arrivals because of the echoing in the shallow water waveguide obscures the individual pulse arrivals from a multi-path ray model, for example. But in the deep ocean, Andre and I did some simulations, and it appears that you could see you only need 14, that's sort of the number we came up with, this 14 hertz bandwidth would allow you to see the individual arrivals at a long range in the ocean. And then there's some cutoff where the individual arrivals get very close near the end of the pulse.
Yeah.
And then no bandwidth is enough for that. But I would be interested in seeing what the problem was in the deep ocean with the 16 hertz, because it seems to me that should have been usable. I know that you were very successful with the 100 hertz bandwidth.
Well, of course,
But-
all is not lost with the 16 hertz bandwidth, but it's a smeared picture.
Correct. But if you know what you're looking at, I think you can deal with the
Yeah.
smear. And I think perhaps we know more about what we're looking at now. And with all the internal wave scattering research and so on, the appropriate averaging scales are known so that you can extract what you need from the lesser bandwidth. I think that's where we're at now.
We're better at it now.
Yeah.
I mean, in the beginning, when they started it, if you didn't see a result derivable, it was useless, right?
Right. But I think now you
But
could
it's
probably do
shallow.
something with the 15 hertz bandwidth.
But in shallow water, that stuff shows, that source shows the modes beautifully. I mean,
Yes, it shows different. It doesn't show. Yes, it's great for modes. It doesn't, and where because it's the correct.
Big Bertha will still be used.
Yeah. Anyway, it's interesting. I just perked up when you said that that bandwidth wasn't enough because we sort of analyzed the heck out of it and thought that would be a useful bandwidth.
See, I'd like to ask a very different sort of question. In your background, we appreciate you spent some time at Manchester
Yes.
and did some things that are maybe considered first in terms of programming and so forth, but I'm just curious about the experience of being there. I guess in the 1950s, maybe still a post-war environment in England, and just what your observations might be on the climate at the university and in the city and generally the society.
Well, that was a different experience, and perhaps, you know, we could chat about that more. The two of us. There was an effort, especially at Manchester, to where they created the first stored program digital computer. They were largely led by several people who had spent as happened in the U.S., who had worked on radar during the Second War. They really had some ideas about storage, which, you know, was really a major holdup. It's a terrible holdup if you're working with vacuum tubes, and they built a store and then decided they had to build a computer to test the store. It was kind of a backward way around.
Oh, memory, you mean?
Yeah.
So they
Yeah.
built a memory system?
Yep. If you we were able to take a box like about the size of a small refrigerator and store 256 bits. But high-speed random access, you could get at it. For myself, myself and a fellow graduate student built the world's first computer using transistors, the germanium point contact transistors. Well, if I may tell you that my favorite story about the importance of asking the right question. In the mid-30s, in England, there was a big concern about aerial defense of the island, and a civil servant in London was asked to write a report about what would be done about air defense. And I guess he was a conscientious man, and he had heard about death rays that would destroy an aircraft or kill the pilot in the sky. So he said, well, I better include this in the report. So he sent off an inquiry to the National Physical Laboratories, where it arrived on the desk of a Scotsman, Watson Watt. And Watt looked at this and sent back a reply, said, you asked the wrong question. He said, don't think about using radiation to destroy an aircraft. Think of using radiation to detect an aircraft. And that was the start of radar. Watson Watt was a frugal Scotsman, and it happened to be the end of the month, and he tore off the sheet on his calendar and wrote this historic reply on the back of that and sent it back to London. Okay.
Great.